Okay, Math 1101, the final recorded lecture to be scheduled for May 3 or May 4, depending on your section. And we're going to spend some time on 8.4, around 3 lectures worth, as we finish up the final section in the class. And it talks about apportionment. We're going to mostly focus on the House of Representatives, but that's also integral in the Electoral College as well. Of course, the Electoral College is made up of all those House representatives plus 2 senators per state. So with a minimum of 1 representative and 2 senators, each state gets 3. We'll talk about the Electoral College another time. This leads into it quite well, but it's not exactly the same. But anyway, the major step here to get started is to find the ideal district size. I believe it's over half a million now. It's quite a lot at this point, but back then it wasn't so much, and we're looking specifically at the year 1810. This all basically started around 1790, but we'll take a look at some of the data from around those times. But the main idea in the beginning is to find the ideal district size. We take a look at the U.S. population and divide by the house size, which has been set at 435 for a while, but a long time ago there were less representatives. And we find out what the standard divisor is. Maybe it's 500,000, maybe it's 30,000. And then that goes into each state's population to see about how many House of Representatives, how many representatives they would get. It's called the quota. And typically there's some adjustments that have to be made, and that's where Alexander Hamilton, William Jefferson, etc., come into play. Daniel Webster, there are a lot of people that had their 2 cents. Even George Washington had something to say about it. Let's take a look at the map. Way back in 1810, we had a U.S. population of around 6.5 million, 6.6 million in 1810. The House back then was defined as having 181 members. That's quite a bit less than now. They've got it kind of locked in for the last 100 years at about 435, as I recall. And so we look for the ideal district size. I'm not too worried about the decimal, but for legal reasons, I believe that's in the Constitution where you actually have to put 3 decimals down, but I'm just going to kind of ignore that. If I could get my pen to work. Okay, why isn't it working? I don't know. All kinds of little situations here. So, okay. Anyway, the pen doesn't seem to want to work. So maybe if I erase, and maybe it'll, okay, then go back and use my eraser. Okay, all right, so maybe now the pen will work when I put down the ink pen. Okay, good. So we divide it out, get about 36,000 per House representative member. So each state's population is divided, and if we look, divided by the 36,000 that is, and back in 1810, Connecticut, which was first in alphabetical order, had a population of only about 250,000. Things have changed a little since then. And so if we look at the 261,000 and divide by 36,000 or so, we get about 7. So 7 looks like a pretty good estimate for what Connecticut would get as far as number of representatives are concerned out of the total of 181. So it's somewhere in the middle of the states. It's a typical average state, I would say. It's certainly not as big as New York, which for many years was the leading state in population. So this may be tough to read. Let's see if I can zoom it without causing issues. We look at the quota to 3 decimal places after we divide the population by about 36,000. And then we look at the numbers and we just do typical rounding. 7.197 rounds down to 7, 1.952 rounds up to 2. You get the idea. Typical rounding, no shocking news here. The only bad part is most of the time they don't match up. If you look at the bottom, the totals, you get 179 on the rounded quota. That is not the same as what we're supposed to have. So 2 of them have gone missing due to round-off error. Yeah, it's a problem with round-off error. So now what do? Different people had different thoughts on this. Alexander Hamilton had a major thought. Turns out he was overridden by George Washington. Actually, one of the homework problems has something to say about that, and that would be kind of a problem for the state of Delaware, as it turns out. But anyway, we have to figure out what to do with how to get those extra 2 seats in there. So here's Alexander Hamilton. You've heard of him. He certainly had a lot of notoriety in the last couple of years with that play everybody's heard about. So the problem arises what to do with the decimal parts. They call it fractional parts. So here's the first method, either by ranking the decimals or rounding the decimals somehow. So what do? With Hamilton, we rank the fractions. We calculate the quota like we just did, give to each state the number of representatives corresponding to the whole number part. Now, this isn't just traditional rounding. We're just going to look at the whole number part and truncate the decimals. Just drop them, at least for now. Of course, we'll be under the total. And then we have leftover house seats, representing the fractions left over, decimals left over. So let me be clear here. Most of us are looking at a decimal situation. Traditionally speaking, that could be called a fraction, like 0.197 is actually 197 one-thousandths. Yeah, that's one way of saying it, but I'll just use decimal. Anyway, we represent the decimals left over as follows. Rank the states by the size of the decimal part of their quota from greatest to least, and give one leftover member to each state in that order until the leftovers are exhausted. So what does this mean? Okay, well, we have to take a look, and although the picture is small, maybe I can zoom just a little bit without causing trouble. Notice in boldface, the higher decimals are going to be rounded up, just like they would have been. And so 1.952. And notice, of course, first of all, we just put down the part before the decimal. We truncate the decimals to 0. We just drop them all, which isn't exactly fair, but it's a starting point. That's all it is. And when we do that, we only have 173 of the representatives designated. So then we certainly take the highest one is Vermont, not Vermont. That's a mistake. And got 5.99. Although it starts with a 5, that's going to be the first one to get its extra seat to make it up to a 6. That's pretty easy. In fact, most of them seem to go the way you expect, except there are a couple of that are not going the way you expected. Virginia is one. That only has a 0.476. North Carolina is another one. That only has a 0.414. But we needed to find the other 2, didn't we? And that's how we did it. We found the ones that were kind of waiting in line with numbers that almost rounded up, and we choose them. First Virginia, second North Carolina. Now those that are underneath it, like Ohio, bad luck for Ohio, they were third in line beyond the natural ones, and so they do not get the extra seat. And this seems to be, at first glance, a fair division, yet there are problems with it. This is why George Washington vetoed the plan. First presidential veto ever, by the way. And the final seats do get you to the 181. You get the extra 8 seats overall, 6 of which rounded pretty naturally. I'm putting dots on all of those. And then 2 extra ones, North Carolina and Virginia, that take up the rest of it. And this doesn't seem to be a bad method, but there, as I say, are some difficulties with it. So let's take a look at an example and see if we can do something with this. City has 4 districts, north, south, east, and west. That's pretty basic. There's 10 city councilors, kind of like representatives, allocated according to population, and we have to have at least 1 from each district. So even if one doesn't seem to qualify for a city councilor, they get 1 no matter what, so no matter how small they may be. So now calculate the quota from each district and use Hamilton's solution to determine the number of councilors to represent each district. Now keep in mind, if it just went normally, we might not even need a special method, but we've just gone ahead and decided to use a special method. So the 10 seats to fill and the population of 30,000 are key. This is how we get started. This is a very simple division. You can do it in your head. The ideal district size is 3,000 because the total of 30,000 is divided up amongst 10 seats to be filled. 3,000 apiece in a perfect world. Well, okay, what we have then is the populations. And the north, we take the 3,900 people, and we divide by 3,000. So all these numbers are divided by 3,000. And when you do that, you get a 1.3. So it's 1 and a little more. If we just keep on dividing by 3,000, we find that east gets 1.6. That could round up to 2 perhaps. West is exactly 6. It doesn't even have a decimal portion. South is 1.1. This is all carried over into the next frame. Let's just go ahead and take a look at frame number 7. So now we don't have the populations in front of us, but we do have the north with 1.3, east with 1.6, west with 6, and south with 1.1. So the initial seats, according to Hamilton, are only the numbers that you see in front of the decimal point. It's called truncating the decimal, sending it off to 0. And of course, it's bound to be less. It's pretty rare that you'd hit it right on the money if they were all exactly the same. Without any decimals, it's possible, but extremely unlikely. We do have to deal with a quota remainder, although the West didn't actually have one. So that's a bit unusual right there. But the quota remainder, we compare 0.3, 0.6, 0.0, and 0.1, and guess what? 0.6 does get the extra added seat. And there's only one extra one because we'll see that we got 9, but we need 10. So there's 1 that's missing. So all we need is to get the 1, and 1 plus 1 is 2, so East gets 2 seats. And by the way, this is exactly the same as normal rounding. In a basic example like this, that is bound to happen, that you could get normal rounding to send you in the same direction as Hamilton. But of course, with the United States, we have at least 13 states and more, up to 50 now, and 51, including D.C., I suppose. And yeah, they don't get representatives, though. That's the Electoral College, separate issue. Anyway, we do have the 9 that turns into 10, and natural rounding can be confused from the Hamilton method. This isn't, they just happen to coincide. It's just a coincidence. But the 0.6 does beat out the 0.3 and the 0.1, and of course the 0.0. So East does get the extra seat. That does seem fair, doesn't seem unfair, but there are paradoxes that work out from this kind of thing. And so I was going to work on another example if I have room on the page. Let's see if I do. Let's see if I can squeeze this in. Perhaps I need to erase first. Let's do a little bit of erasing, and I will erase this stuff here, and I'll go back to drawing. Okay, so now in the example, to try it yourself, we have the north, the east, the west, and the south. I will just abbreviate this. Looks like news. And the populations were, as you can see in your book, 3,900 for north, 4,800 for east, and 18,000 for west. So west really has a lot. And south has 3,300. Okay, there are 20 counselors, so we have to get 20 of them involved. So we first of all find out what the grand total of the population would be. That happens to be 30,000. So I've run out of room. Let me go ahead for this example, say 30,000 is divided by 20. That means the ideal district size for this example is 1,500. So more seats to go around. You only need 1,500 people to do it. So next step, divide by 1,500. I'm writing at an angle. Sorry, it's so sloppy. And just do it for every single region or district, wherever you want to call that. And so 3,900 divided by 1,500 would initially give for the quota 2.6. So this is the quota column, and 2.6 would be the number. We'll just copy them down now. 4,800 divided by 1,500, 3.2. 18,000 divided by 1,500 is exactly 12. Once again, West doesn't have any decimal part to speak of. And then 3,300 divided by 1,500 is 2.2. Okay, so now we have the initial seats. The initial seats come over here and just pull off the number in front of the decimal place. 2 from the 2.6, 3 from the 3.2, of course 12 from 12.0, and then 2.2 becomes a 2. Well, if we have 20 seats, let's add up and see what we have so far. 2 and 3 is 5, and 12 is 17, and 2 is 19. We're missing 1. 1 more has to be allocated. So now we look at the quota remainder, which is under this column. We just simply look at the decimal. We're splitting off the whole number from the decimal. They call it the fractional part. The 6 is clearly the winner. That's the added seat. And then the 2 from the initial seats plus the 1 equals 3 seats. Now, the rest of them get to keep what they got. They don't get any extra boost, certainly not West, because they had nothing to get a boost from. And then 3 for the East would happen, 12 for the West would happen, and 2 for the South would happen. And of course, you add these up, that extra one gives you a 20, which is what you need to have. So that's the plan. You find out what the ideal seat size would be, district size would be. And whether it's 3,000 or 1,500 or some other number, 500,000, 700,000, whatever it might be, you divide each of the districts or states or whatever they may be by that number. You find out what the quota would be, including a decimal point or 2, and drop the decimals for Hamilton. Keep the whole number only, and then pick out what you need from the list of decimals that are ranked. These are ranked decimals. Now, I've not put like first place or second place or anything like that. Hamilton does have a bit of a problem with ties, though. They do mention that one of the homework problems. If, for example, we needed 2 extra seats and East and South were exactly tied, which they happen to be, of course, I got to push that, then we would have a tough time deciding which one would get it. Would it be East or South? Now, in reality, that would practically never happen. With millions and millions of people, the likelihood of a tie is virtually impossible. But in small districts like this, becomes more likely a tie could occur, and so that's where another weakness of Hamilton shows up. So none of these methods, once again, are perfect. They all have advantages, and we can talk about the current method later on that will not be in this lesson. We're going into the history books for this right now. Okay, we have various things. First presidential veto was talked about in the book. It was, let's see, revived in the 1850 census, and so it actually came back. The Hamilton method was actually used, but they had to wait a while to get to it. They tried Jefferson's method first. He was the 3rd president of the United States, and he was also very interested in this kind of thing. So a lot of people, no matter what their positions were, they were all interested in how to allocate the votes, and they all got their names in the history books. There are more than we could mention in this class. But Jefferson's solution is a little bit different, and his way was in effect from 1790 to 1840, the censuses that followed those. So starting with the 1850 census and the election years that followed that, and just the dividing of the Congress, which is also being done at the same time. You got 2 different purposes for this at least. So Jefferson's solution is adjusting the divisor. It's an adjustment, and there are spreadsheets and complicated formulas that the book mentions for this, but we're not going to break into those. We're just going to take a look and see how that would go by trial and error. So we're going to just do the first step and see if we happen to hit a bullseye. It's possible but unlikely. We'll make an adjustment or 2 or 3, and then we'll come up with an actual total that works. So we have to adjust the divisor. It isn't like ranking the fractions or decimals. Let's see what we're talking about. First of all, we use the ideal district size as a divisor. This is just the same as before, no change at all. And then we calculate the quota for each state by dividing the population by the divisor. So far, these are exactly the same. And looks like we round down each quota to the nearest whole number, but not less than 1, and sum the rounded quotas. So this part looks almost the same as before, except Jefferson did say not less than 1. Hamilton didn't say that, so technically they could have given 0 seats or representatives to a very small state. Some people might say, oh, that's a good thing, but that isn't exactly fair. Sometimes people in smaller regions get higher representation than normal. We can talk about that later on, but as it turns out, it doesn't make sense to be less than 1. So that's what they wound up doing, and Jefferson made sure that would happen. And his way was in effect for the first 60 years or so of our country. Anyway, step 4 says that the sum from step 3 is larger than the size of the house. Ironically, if it's larger, you increase the divisor. Seems like we're headed the wrong way, but remember, these are inversely related. If you increase the divisor, you divide by a bigger number, your result is smaller. And yes, we want it smaller. If this sum is larger than the size of the house, we need to shrink it by increasing the divisor. And similarly, if the sum is too small, we need to increase it. But the way to do that is to shrink the denominator, decrease the divisor. And that will make it grow. So these are inversely related. If you divide by 2, that's one thing. If you divide by 200, that's another thing. Increasing the divisor results in a much smaller result. So they're inversely related. So if you've got one issue, you just simply do that same thing to the divisor. So if it's larger, you increase the divisor. If it's too small, you decrease the divisor. That actually has the desired effect. The process is repeated until a divisor is found for which the sum of the rounded quotas is equal to the house size. All the examples we gave you, and pretty much all of them in real life, can be done within about 3 steps. And yes, there are complicated ways of doing it, but we don't need to know about them. It turns out they're not particularly useful in this particular case. So here we have a situation with the same data from 1810. And they've gone ahead and used the divisor of 36,377 and some change. And so far, these are exactly the same as before. The population, the quota, and then we round down. That part's just the same as before. We're missing a couple. And this is where it stops. This is where it changes. I'll put it this way. So this is the dividing line. So we, instead of using 36,000, we arbitrarily pick a number that's close to that number. You could have picked 35,000, but they thought they'd humor us and try 34,000. You divide everything by 34,000. Let's take a look at Connecticut, for example. 261,818 divided by a new number, 34,000. And on my calculator, let's find out what that would be. 261,818 divided by 34,000. And that value is a 7.700. So 7.7 still gets rounded down. They did not show the particular work there, but it still becomes a 7. So the idea is to break out of the 7s and get into the 8s. Didn't quite happen here. But some states did. Notice how close Delaware was? It was at a 1.95 last time. And you divide that by a different number, and it clearly goes above the 2. Let's just check it out for Delaware. Notice its population, 71,000, and we'll divide by 34,000 just to see what happens. Of course, this was Connecticut, CT, and Delaware. I believe that's DE for Delaware. Okay, so let's just see what that is. 71,004 divided by 34,000. That's a value of 2.088. Wow, just barely crawled over the line here, 2.1 approximately. So yes, Delaware gets a seat here. How about that? And Georgia gets a seat. In fact, several of them get seats. So let's just take a look. Georgia got an extra one. Kentucky, Massachusetts. I'm comparing these two columns, the third and fourth column here. And New Hampshire, so many of them get an extra seat. New York gets a couple of them. North Carolina, man, all the big seats are getting richer. Tennessee gets one. Vermont gets the extra seat. So we've gained quite a bit more, an extra 8. In other words, we're 6 over. That's too many. So instead of starting to tinker with the, ranking the fractions like Alexander Hamilton wanted to do, they simply change the divisor. It's too big. We're 6 over. We increase the divisor. And here's where they pick the number that actually works pretty well, 35,000 as the divisor. So let's go ahead and pick that one. And that's the divisor. Then various things change. And then we can round down like Jefferson always wanted to do. Special rounding rules where you round down. And but we have to take a look at some of the divisions by 35,000. So let me look at Connecticut just as a ballpark example here. Divide that by 35,000. Looks like that's kind of locked in on the 7, so that one's not very interesting. But 261 divided by 35,000 gives us 7.48. So yeah, that still becomes a 7 as you round down. What about Delaware? Delaware is kind of bouncing right around the borderline here. So if I pick 71,000, almost exactly 71,000, and divide that by 35,000, what happens is that's going to be more than a 2, I can tell by looking. 71,004 divided by 35,000. That's 2.03. Barely made it. They're in the 2s. They get to keep their second seat. So that one actually went up. As we compare these columns, Delaware did come out ahead because it was so close to getting that second seat already. And if we compare the third column to the fifth column, there's a lot of ties, but Massachusetts does gain one, going from 19 to 20. And then it turns out that New Hampshire gains one, we have New Jersey the same, New York gained one, Pennsylvania gained one, and so many of the others stayed the same as compared to the quota rounded down method. Now, we had to make up some ground, and we did, and we got a total of 181 on that attempt, so that was actually a good thing. They're saying they compared Jefferson's method to Hamilton's method in the book, and maybe I'll get around to doing that, but it turns out that Jefferson gave one less delegate to New Jersey, North Carolina, and Tennessee, if you compare the two methods. And Jefferson gives an additional delegate to Massachusetts, New York, and Pennsylvania. So the point is, we get our bottom line exactly where we're supposed to. So that's good news. We got the 181 that we were supposed to. And when we see the total matching, we can stop. The divisor does not have to be recalculated. In the book, they say that any number between 34,856 and 35,037 would have given you the same result. So there's typically a pretty large window of opportunity there. It isn't like you have to thread the needle and let's pick a number. And you guess what number? Anywhere between 1 and a million. That would never work. But here, if you go by thousands, you're very likely to hit it pretty quickly. This was on the second attempt. I've never seen it go past a third, and typically you can get it on the first one almost. So, yeah, these numbers are not meant to be particularly frightening. They're just meant to be stuff that has happened in the past according to our country's use of these systems for delegating the fairest way of allocating the House of Representatives, which is a microcosm of American people, those that are involved in the census, of course. So we do have that kind of thing going on, and we see those that kind of came out ahead on that. So I do see Georgia gained a seat, Kentucky gained a seat. Turns out this is no wonder. This is a mistake. This is 173. There we go. I knew there was an error somewhere. 173 is a typo. So yeah, a lot of seats were gained. 8 of them. So did I check off 8 of them? I only checked off 7, so I must have missed one comparing the two columns. This is no big deal, but Virginia also gained a seat. So largely, the bigger states have a bigger sway, and that might explain the paradox we're going to get to. And so they're a little bit more likely to gain a seat just because they have a more weight to carry around. But notice Delaware, the smallest one at this point, gained a seat too because it was so close to the borderline. And part of the reason George Washington didn't like the Hamilton method is because it gave Delaware too few seats, and we can go into detail on that another time. Okay, let's look at this example. Given populations below from the previous example, same numbers as before, let's try Jefferson's solution now and see how that turns out. And there's 10 counselors, and we'll see how that works out. And 10 counselors, a population of 30,000, just like before. We have an ideal district size of 3,000. And that's our first divisor. So they assume that we'll be probably doing this more than once. So there's your 3,000. And everything gets divided by 3,000. I believe we've done this already, so nothing shocking will occur. This is in many ways just a replay of what happened before. So quota using the divisor of 3,000. And here's the table representing Jefferson's solution. And each attempt of apportionment, the quota is rounded down. Okay, so using 3,000, we find all these numbers that do add up to 10. But of course, you can't allocate a portion of the divisor. It isn't like, the East gets 6/10 of a delegate, so the first 7 months of the year they get an extra delegate and then they lose some at the end. That just doesn't make a lot of sense. So there's no timeshares on these House of Representatives or delegates, whatever they may be for. So we round down, which is going to decrease our numbers down to 9. But then there's 1 missing that we still have to take advantage of. We have to give them to somebody. And so now what we're going to do is we're going to change the divisor. We're not going to make 3,000. You could go all the way to 2,000, but you may be way off. So they chose to go to 2,500. There's no right answer here, but just go in easy increments away from what you had, and that should be pretty good. Okay, so when we divide 3,900 by 2,500, you get values like 1.56. So here are the actual decimals that they did not supply to you. 4,800 for the East divided by the new 2,500 So I section this off this way, gives us a value of 1.92. The west, 18,000 divided by 2,500, yields a value of 7.2. And the south, with 3,300 dividing by 2,500, gets us a value of 1.32. I could say 7.20, I guess. And then we round down. 1.56, of course, is a 1. 1.92 is surprisingly, perhaps, especially the east, goes all the way down to a 1 because they didn't quite make it to the 2s. 7.2 becomes a 7, and 1.3 becomes a 1. So the net effect was that the west gained 1, and yes, we do have R10 available. The west had more population, and there's more of a standard deviation, I guess you could say, and it's going to sway a little bit more than those tighter, smaller states. Okay, a desirable trait of any apportionment. Actually, let's take a look at the other example. Let's be sure we tried the try it yourself on this. And the try it yourself says, for the same city, districts, and populations, use Jefferson's method to apportion a total of 8 counselors. And all you need is 1 decimal place according to what they're saying. So let's see what we have. We've got the same population, and now we only have 8. So we have 30,000. For the ideal district size, we divide that by 8, and we find that 3,750 is now the ideal size. So we use that, and we divide everything by 3,750. So let me just squeeze it in down here, NEWS, and the population, which is right in front of us this time. Everything is divided by 3,750. And the populations, let me just see if I can jot them down without scribbling too much. 4,800 divided by that number, 18,000 divided by the number, so it's really the same population, sort of a piggyback problem. And when we divide 3,900 by 3,750, we do get a 1.0. That's a quota, just a 1 decimal point, because that's all they needed. 4,800 divided by that number, 3,750, gives us a 1.3. 18,000 divided by 3,750 yields a 4.8, and the south, you divide it out and you get a 0.9. Okay, this is an interesting example because the first try is the quota rounded down. And 1.0 has no trouble rounding down to a 1. 1.3 rounds down to a 1. Even 4.8 rounds down to a 4, and you might think that 0.9 would write down to a 0, but no, Jefferson thought of this one. They get 1 by default no matter how small they are. I think of Wyoming. I have a friend who lives in Wyoming. Well, anyway, yeah, so we get all of those, including the bonus one for the south, just because they kind of fell below the minimum. They still get the minimum. So 1 and 1, it's a total of 7. Only 7. We need to get to 8. Remember, there's 8 counselors here. So instead of 10 counselors, we have 8 counselors. So we need to add 1, and we have to redo the divisor. So we can divide by another number. We could try dividing by, I don't know. I didn't jot down a number here, but if we picked, say, 3,000, what would happen? So if we divide by 3,000, so I try to piggyback this example on top of the other example, 3,900 divided by 3,000, or the second attempt here, would give us a 1.3. 4,800 for the east divided by 3,000, that's 1.6. 18,000 divided by 3,000 would give us a 6.0, and 3,300 divided by 3,000 gives us a 1.1. Dropping the decimals, you get 1 and 1 and 6 and 1, but that's a 9. That's too much. Oh boy, so that is an issue, huh? We need to get another number in there. How about 3,500? We already used up the 3,750, which is the ideal, which is off. And when I try 3,000, nice round number. If I try 3,500, I'm going to need my calculator for these. So I'll take the 3,900 for this next attempt and divide by 3,500. I'll do the north first. So 3,900 divided by 3,500. That's a 1.1. And then continue, just divide everything by 3,500. 4,800 divided by 3,500 gives us a, let's try again, divided by 35, that is a 1.4. And then 18,000 divided by 3,500 is a 5.1. And then the last one, 3,300 divided by 3,500. That's less than 1. Happens to be 0.9 again, but that one gets a 1 automatically. So that one gets us a 1. Everything else gets truncated. 1.1 becomes a 1, 1.4 becomes a 1, 5.1 becomes a 1, becomes a 5, I'm sorry. And then we have our results as 1151, a total of 8. That's exactly what we were looking for. So whether you pick 3,500 or some other number that's close to that does not matter. The idea is to get these to round in the correct ways, typically rounding down unless it's below the minimum of 1, which is a special case. So the 3,500 is what we needed to divide by, and that's how we get our result. Let's go on to the next example. We hint at the desirable trait of any apportionment is to stay within quota, meaning, that does sound a little vague, but the final apportionment from each state should be within 1, either way, on the high side or the low side of the quota. So the final apportionment should be the quota either rounded up 1 or rounded down 1. So it should be in that little narrow window for it to be fair to everybody. And apportionment methods that do not stay within the quota are said to violate the quota. The Alabama paradox came along when we calculated the quota for certain states. For a house size of 299, which was in effect back then, around 1850, I believe. I'm not sure what the year is for this. 1870, 1880. Yeah, this is 1880, so this is more recent history. And as it turns out, for the house size of 299, Alabama would be allocated 8 representatives. But here's the weird part. We add 1 to the house size, and Alabama loses representatives down to 7. That's not intuitive at all. In fact, it looks like there's something nefarious happening here. However, the math just happens to break a certain way, which is very strange. So this is Hamilton's method. The paradox is involved. So, okay, we're going to use Hamilton for this, and let's see here. Explore the Alabama paradox. For a house size of 299, determine the ideal district size and verify the quotas for Alabama and Illinois, that is, and how the decimal parts of the quotas compare, how the decimal parts of the quotas compare for 300 members, because there was some issue as to how many seats they were going to put in. They used to actually increase the number of seats in the House when they had new states, but that has not happened in quite a while. It's been about 100 years since they've done that. So let's see if we can take a look at some of the data here and see how it turned out. This is a very strange one. I may have to talk about this one in the live classes coming up as well. And this might be better off looking in your book or your ebook, because this is very fine print. We're mostly interested in Alabama. And this is the Hamilton method. So let's make sure we see it's the Hamilton method. And when we divide it by 299, well, let's go ahead and see what that would be. The ideal size, actually they say it here in the book, is 49 million divided by 299, which gives us about 165,000. So here's the ideal for 299. As you divide the population, which is about 49 million, and divide that by 299, we get an ideal district size of, I'll just round this slightly, 165,121. It was still pretty small back then. And then we can divide that by 300, and we get a little bit of a different number. And let's see what that would be. As we divide by 300, we have the following. That's about 49,371,340. That's the exact population back then. Dividing by 300 yields an ideal district size of 164, a little bit less because there's one more representative in there, 571. So this has gone down by about 600 or so people per representative. Well, anyway, I'll explain this more detail later. Alabama had a quota based on the 299. As you divide the 1.2 million by the 165,000, so let me just show you for the 299, the steps that we've already done. 1.2 million is divided by the approximate number for the 299. That works out to be 7.646. Hamilton's method Certainly we don't ignore that part. That's the quota. And it would be given an extra seat because as you look at the boldface, which is difficult to see on this small screen that I have, that one actually qualifies as a boldface number. It's actually one of the last ones that qualified as you rank the fractions. In fact, it was the very last one. You might not be able to see this, but the Illinois measurement had a slightly less number, and it does not have an added seat. So this one was a bit stricter. Last time we got into the 0.4s and still gave seats away. Here we stop at 0.646. Alabama kind of got lucky with the 299. But the luck doesn't hold when the house size gets to be 300. It just doesn't hold at all. So then we can look at the 300 and see that the population, which has not changed, divided by the ideal district size, doesn't seem to have too much effect. At first glance, very little effect. 7.671. It's about 1/3% more. And it looks like it's gone up, so how could it go down? If you're ranking the fractions, it just so happened that some of the bigger states with higher variability, naturally speaking, happen to push their weight around a little bit more and actually got some higher level situations, round up in their favor, in other words. And so now look at Illinois, just because we're interested in comparing Illinois versus Alabama. Those are the two, so I squeeze my pen, that we're mostly interested in. Okay, let's see. Okay, now it's not working. I just charged the battery too. Okay, so we've got Alabama versus Illinois. There we go. Okay, good. And now look at Alabama's quota, 7.671, but Illinois, don't care about the 18, but Illinois has a 18.702. And it beats the 0.671. Narrowest of margins, but it actually happened. So it's still called the Alabama paradox. And then Hamilton's method was eventually completely discredited and thrown out. It just doesn't seem right for this to happen. So Alabama did not get the added seat. Illinois jumped ahead of its place in line because Illinois is simply a bigger state. The bigger states had much more of a propensity to swing their weight more wildly as a new factor comes in. And essentially what we're doing is we're multiplying by 300 over 299. I can explain the algebra another day, but that does change all the quotas up a little bit, so they all increase. But with this ranked fraction idea, they're kind of jostling for position in unpredictable ways, except for the fact the small states kind of stay in they stay in their lane, and the big states wildly skip across lanes. That's one analogy I can use. So the Alabama paradox is rather strange, but the fractional parts are what rules when it comes to Hamilton, and Alabama just wound up losing out in this particular case. Now, I don't know if that exactly happened or what, but they have another problem we can get to later when we have more time. Anyway, this is just saying what we just said. For the 299 situation, Alabama had a divisor of 7.646. Notice we're only looking at the decimals. They call it the fractions, but I call it the decimal. And Illinois had a 640. So Alabama beat them by just a little bit. 0.646 is indeed greater than 0.640. But that luck wasn't going to hold if they increased the size of the house, which is something beyond the scope of this class. And so Alabama had the larger fractional part. But with 300 members, and I do not know what happened historically on this. I need to look it up. The fractional part changed. Illinois swung a little bit more wildly, and Alabama did not. It stayed in its lane more. Illinois suddenly leaped over Alabama, stealing a seat, so to speak, from Alabama and gaining a seat for Illinois. It's apparent that increasing the number of seats changes the fractional decimal parts of the quotas for the two states. Hamilton's method allocates leftover seats according to higher fractional parts. It is reasonable that Alabama could lose a seat and Illinois could gain a seat with the change. Perhaps this was done hypothetically, but it still was quite distressing when people started looking ahead. And there were warning signs 10 years earlier, but 1880 was, I guess, the final nail in Hamilton's method. And there are certain other situations, too. Ties are not good, and if you don't have a certain minimum of one seat, that's another issue. So we covered some of the deals, and we'll cover some more. I'll get into some of the homework problems. I'm sending out, of course, a list of suggested book problems that I hope that you will be doing. I know all the better students will be doing them, and mostly they'll have answers in the back, although I'm afraid not all of them do. but be sure to email me if you'd like, and I can discuss some of the stuff with you. And be sure to work on those, and certainly work on your WebAssign. And good luck with all of that. And I'll be back live, of course, Wednesday and Thursday next week, and those dates are May 5 and 6, and we'll continue with 8.4 for a couple more times, and then we'll have an entire day of review for the final. All right, that's all I got for you. So have a nice weekend, or have a nice few days coming up here, and we'll talk to you later. Bye-bye.